So the E200, I can see if where's the micro E200. See if that's oh, those are still 32-bit, but you know, 64-bit stuff is 32-bit, at least user space compatible. I don't know.
I had one more question related to this, and I haven't researched it enough yet. I thought it might be easy if I ask you. You might be able to guide me in a direction. And that was regarding the endianness. So,
right. Yeah.
So as far as I understand, like the PowerPC architecture is bi-endian, so it can run in either modes.
Correct.
And the address translation and all of that is dependent on like which mode do you use. So let's say if I were to go with the default support that's available in the Linux kernel and all the build root or Yocto or any of those tools, it would be, I think the prevailing standard nowadays is little endian.
Yeah.
And what we should get out of the box, let's say if it's already inbuilt, would be little endian. Memory translation, we don't know yet if it's like to what degree to support it, but it'll be by default run in little endian mode. And if we had to do like those memory tables and translation tables, then we are okay with going ahead with little endian mode and just a patch that takes care of that.
Right. So I think if you look at the MMU for microwatt, you do see that all the data from the tables, even though the Linux kernel, I think for the for the more recent processors, we switched from big endian to little endian. A lot of the things like page tables and stuff, the data still seems to be in a big endian format. So it's doing a byte swap, for everything that it reads from those tables inside the MMU. At least that's what I can see in the in microwatt, and for as far as I understand, that's running a very recent kernel. So I was slightly confused by that because, I thought that maybe when we went to little endian with Linux for PowerPC that we would have done so wholesale, including these tables, but it, yeah. So this processor here, the E5500, I think that would be pretty close to to A2O in terms of architecture, which generation of architecture it was.
Okay.
I think it is this book. Oh, book.
I guess E6500 is also quite similar to E5500.
Yeah. I don't have a. I was trying to find whether it says here whether it uses Bookie. I'm guessing that it uses Bookie. Yeah, I would think that if one digs through this a little bit, you'd find that this is boogie.
I'll look it up. Yeah. Yeah. So this is something I will research like a bit more today, and maybe tomorrow, and then I'll try and flash it irrespective and see what works, what doesn't work. There's just a whole bunch of updates to the Vivado tickle files and scripts that I had to make that I'll push in our new GitLab project. The biggest change was that I basically made the entire project scriptable, so you don't actually have to start Vivado UI to do some changes. Everything can run as part of like a command line script from start till the end.
Nice.
To get the bit streams and build a project. I think it's just a nicer flow from like if you want to do like a CI/CD kind of thing. Eventually, we can just run the whole thing using a script. But it's just like a bunch of changes to those files, and there were a lot of warnings there, which I wasn't sure, if they mattered or did not matter. I can share some of those in the Slack channel, but it looks like it's just the default way Vivado works. It'll give you like a whole bunch of warnings, but they may not be like very critical.
Right. Yeah, and there could be things, in the language itself that have been, are sort of getting stale, right? So it's well, with VHDL, I know that this is Verilog, but with VHDL, I know that is the case. That there are, certain constructs that you get advice no longer use them, right?
Yeah.
Maybe Verilog is more stable. Yeah, and if it doesn't, if it doesn't look like this is, a similar thing ISA wise, then ping me. I think the person actually who can probably help you the most is Paul McCarris. Because he's been upstreaming things, and if you get to a point where I need to make an introduction, I'm happy to do so. Paul is very happy to answer all kinds of questions, but he is retired, so he doesn't he doesn't work every day. Yeah.
Thanks, Peter. Yeah, I'll start with it today. I'll keep you guys posted, and I'll reach out to you if I need some support there. Thanks for the offer.
Sure. Yeah, wonderful. And again, congratulations on getting through this.
Thank you, Sanket, for putting a lot of time together on this. I think this is really going to be very helpful.
No, this is
you
have to get through these barriers one by one, right? Being able to build is a big one.
Yeah. The building is a very painful process, actually. Now we have Sanket. So, so Peter, today, what is it you wish to cover?
So I thought we might look at the MMU code a bit.
Right. Yeah, maybe we can.
I can share that. I I won't claim that I understand every line of it, but I did stare at that for a couple of hours. So that would probably be helpful for Ati. Yes, so maybe before we do that, maybe Ati wants to say something about what his experience has been.
Okay, I did my fair share of homework.
Good.
Yeah, I looked up these YouTube lectures by a professor in TU.
Oh yeah, Onur Mutlu. I saw that.
Yeah, I
he's a
saw
good guy.
all 4 hours of it, and I have the what's the gist of it part, which is required for me.
Right.
So now I'm kind of getting what you said back then in the previous week.
Right.
This part, the virtual memory part, getting into the page number and getting
Right.
decoded as the physical memory location address.
Yeah.
So that's kind of similar. I looked at the code, but I didn't have my ability enough to figure out. But I figured this out in an outline.
Yeah.
It kind of looked like this, but I didn't get the whole entirety of it.
Okay. Yeah. So I think last week we looked a little bit at how the access to the iCache worked, right, and also with the 2-entry ERAT, right, or basically an ITLB, because this segment. Yeah, I mean, if you get stuck there and we need to go. So today I was going to look more at the MMU, and I don't know that those 2 lectures that you picked up, would have talked a lot about the MMU. I didn't listen to them.
I will iteratively.
It's still probably mostly about. Yeah, it's mostly about the caches, I would imagine, right? Those 2 lectures.
Yes.
Yeah. So today I was going to look. Right. Yeah, if we need a session between us, I'm also, I don't, I mean, I think it's the MMU is somewhat important, I think, to ultimately, I think we will need to understand that in detail, right? Because I think the MMU we basically want to bolt on to A2O. So we're really going to have to understand, its interfaces and everything. The way the cache is done in microwatt, is probably a little bit different than the way the caches are done in A2O. So I think if we really dive into detail, maybe we should do that on A2O. So maybe what we should put on the agenda tentatively for next week, and I can yeah, I might have I might be on a very short vacation next week, but if I am, I'll leave some slides, and I'll try to give people enough advance warning. But that's, to me, seems logical that would be the next thing to look at, right? So we look a little bit at the MMU today. Then next week we begin to look at how the caches are organized, and where the TLBs and or ERATs sit in A2O, where the MMU is, what interfaces it has. And then I would dive, deeper into that. But we're not going to transplant. At least I don't think so. I don't think we're going to transplant a cache from microwatt into A2O. I think the only thing we're going to try to transplant is the MMU. So in that sense, understanding the caches on microwatt is more, it's really more of just an exercise. But I wouldn't worry too much if you don't end up, understanding all that. But I'm glad you looked at those things from Onur. He's I'm not familiar with these two lectures in particular.
One doubt. We will do the radix page table, but not the caches. I'm not getting that part.
I'll start again with the picture for the radix page table today.
Okay.
Yeah. So actually, let me see here. Something else. Okay, I'm going to just share my screen. So this is the page, the picture I showed before, right? And it's I posted these PowerPoint slides also in the in my GitHub repository, this describes how the address translation works. So if if I come up with a virtual address, right, and I don't have, and really in case of Power, you would call it an effective address, but I don't have a translation for it. I've missed in my in my translation caches. So now the MMU is going to get asked to find a new virtual to real translation for that pointer, right? And it's going to do that by going through the various tables here on this page, and when we look at the MMU, we'll see things kind of happen in this order, right? So the first thing is you're going to access the partition table, and this is based on the partition ID, right? And then you're going to get an entry from that is pointing to the process table, right? And then and that one is indexed by the PID, by the process ID. So this is the logical partition, this is the process. And then you're going to get pointed to a sequence of table. And actually there is many of these tables, right? So each entry here would point to a different sequence of these tables, and here also each entry can point to its own individual next one. But once you're here, then you have a table, and this one you access with some of the bits from your virtual address, right? That you're trying to find a translation for, and basically. So you take some of those bits, then you get an entry from this table, so it points you to another table. You take some other bits from the address, and that's going to point you to some entry in the second table, and then you again take some other bits, then you go to the third table, the fourth table, and then ultimately you end up with with the address of with a physical address, for a page in memory. So to this process here of going through these various tables, that's what happens in the MMU, in the memory management unit. So the new translation, which is a combination of the virtual address, the physical address, and the page table size, needs to get installed in a new TLB entry in whichever TLB needs to be updated. So does that piece make sense so far?
Yes, Peter. Very good. Yep.
Yeah. Now, I mean, it is, all the bit manipulations in this is, kind of intricate, and we're not. So the code for the MMU is, it's not huge. I think it's maybe 600 lines of code or so. It's not tremendously big. But there is there's of course a whole bunch of intricacy in the bit manipulations there. Okay, so then let's go to the to this here. So first, well, okay, let me go to the MMU. Right, so of course it has a clock and a reset, and then you have the basically the commands to the MMU come from the load store unit, and then ultimately the MMU is going to message back to the load store unit when it's done, and then there is also an interface to the data cache as well as to the iFetch unit. Because there's a TLB over here, and the data cache actually need for two reasons. The first one is that as you walk through these tables, right, you're going to have to do your own loads and stores from those tables, right? So that's why you need to access the cache. And the other one is that there's also a translation table over there. So something that I also mentioned last week, but we went over it a little bit fast, so let me go back to it, is there's this file called common.vhdl, right? So you have these types here, and they're defined in a file called common.vhdl. So here you can see what that interface from the load store unit to the MMU looks like. So it actually there's a variety of commands that might happen, which includes SPR access. I think one of the SPRs that lives in the MMU, I think, is the process ID, and then there might also be instructions like a TLB invalidate entry, or things like that. But for our purposes, the main thing is that you know, if we have a valid command coming down within an address, then it's, you know, we're asked to provide a new translation for that. And then, you know, after all is done, the MMU is going to signal back to the MMU that it is done, and there is to the load store unit that it's done, and there you know, if the tables in memory somehow don't have the right structure, or if something goes wrong, then you know, it would also report an error condition back. But in, you know, most cases, hopefully it's just going to report that it is done. And then you know, there is an interface to the data cache and to the fetch unit with the ITLB, and here's a DTLB in there, right? And you know, through that interface, the MMU can ask the thing to do a TLB invalidate entry, do all, is probably a TLB invalidate all. It can add to load a new translation into the TLB, and then, you know, when it installs a new entry there, right, of course it provides the address, you know, the virtual address that translation is for, as well as the page table, you know, the physical address, the page table entry that thing translates to, right? And it's the same on the fetch side. The only difference is that on the interface to the dcache, you know, it serves a dual purpose, right? It can either ask it to do some manipulation on the TLB over there, right, and validate an entry or multiple entries, or load a new entry into the TLB. But it also can access the data cache just to try and load something. So, you know, and I think that address is used here for two purposes. You know, either to load something from the data cache, or if it's a TLB entry, then, you know, this address is the virtual address, you know, of the virtual real address pair that gets installed into the TLB. And then, you know, this one does, you know, communicate, has a communication path back, right, to provide the data back. I'm not exactly sure what the purpose is of stall, right? But when it's done, you know, I assume that's when the data is valid, right? It provides the data back that you've asked for. And of course, if there's an error, then it'll provide the error condition. So that is a quick description of the interfaces. Right. So that's what's behind these interfaces over here. And then the way this thing is set up is basically, it's you know, it's kind of it's a state machine, right? So depending on you know, what is being asked, you go through these different states here. So for example, you know, and remember this picture here, right? First thing you're going to do is read the partition table, then you're going to read the process table, and then you're going to walk through these radix page tables one by one. And if we look here, right? So there's a set of states that has to do with, okay, I have to read the partition table. You know, of course, I have to you know, to wait for that result to be done. Then, you know, I go to a state where it's having read the partition table is finished, then I have to, after that, I have to read the process table. There's that can take multiple cycles as well. So there's a state in there where you're waiting. I don't know exactly why there isn't a done state. We can look at that. Maybe it transitions after that directly into this segment check, and then it goes into the radix lookup. I think it must go through these states, 4 times, right? And then ultimately, when you've handled all the bits of your virtual address that are used for these radix table lookups, then you go to the state radix finished, and then I think it goes to a general done state, and then it signals done back to the back to the load store unit. So as it goes through these different states, it'll build up the addresses for these for these different entries. To be honest, I haven't completely figured out what this page table 0 versus page table 3. I know you're using 1 if bit 63 of your address is a 1 and the other if it's a 0, but I don't know. I don't know what the difference is. And then there's a shift amount. You need to shift, in order to access these tables, especially when you go through the radix tables. You're shifting your address. You're masking certain bits out. Those kinds of things. And then yeah, so this thing here is the shifted, shifted bits from the address. And then yeah, this is just an initialization. So within this code, right? So as you go through these different state machines, all of these things here, all of these blocks, right, get evaluated in parallel every cycle, right? And the the command from the from the load store unit ends up in this in this L in which gets copied to sorry, I think LN goes to RN, and then RN goes to, let me look at RN. So this is the so our normal operation, it probably turns into text. Okay. Kind of error it was, and this shift amount, you're doing it based on different bits of your so is you're working on, and this process here actually produces that.
Yeah, I was away. What happened actually? Did Peter leave or?
His signal dropped, I think.
Oh, he'll be back then. Okay, just wait. Oh yeah, Peter, are you able to hear?
Yes, I am. I don't know.
Yeah,
I don't
no,
know if
now
something
you are okay.
broke
It's
on my.
clear.
Yeah. I switched to my cell phone network, so I was probably in the middle of something that I lost you. I'm sorry, I didn't immediately realize that I had lost you. So let me go back to the to sharing. Okay. Okay, so I think this piece you still heard, right, about the interfaces into the MMU from the different units. I hope that part.
Yes.
I was okay, and then I think also the part of talking through the different states that it goes through, right, and how it relates to this. I think hopefully that was also still before I lost the network.
The part till dcache to MMU and code comment.vhtl at code line 610 till that it was clear.
Okay. Yeah. So basically this thing, right, is a state machine, right? So at any point it is in one of these states. There are two things that it can be asked to do. It can be asked to do a TLBIE, or it can be asked to do a translation. right? So if it's asked to do a translation, it'll go into the process here, right? So you'll read the partition table, the process table, and then you'll go through each of these 4 levels of the radix page tables. And the states that are associated with that are these states here, right? And things are actually broken into several stages where first you sort of enter that stage, and then you're in a waiting stage. I think typically waiting for data to come back from the data cache, or beyond if you end up missing in the data cache, and then you're done with that, and you move on to the next thing, right? And for the radix part, you actually have to go through it a number of times, and as you go through it, you build up, these various addresses that are basically correspond to these pointers here. And then this is just initialization. This piece here is mostly just reporting. It doesn't really do anything, but it actually helps you understand, right? That kind of the different functions, right? So if this R invalid is 1, so this is probably some copied version of the valid that is in the this valid here, right? So that eventually ends up there, and that means that we actually got a TLB miss, and we have to go translate this RN address, right? This is at the very end when you're done. So you send a done signal, from the MMU back to the load store unit. If there's an error, then you let it know what error it is. And when you're in the middle of doing these radix lookups, this here, you keep track of the shift amount, right? Because you're going through that 4 times, each time with different bits from your from your address, and that shifted address, is this here generates that shifted form of the address that you're translating, and there's masking bits. I'm not going to walk through the details of that. This here is just initialization, and then here is kind of where things begin to happen, right? So if you get a command, it could be a TLB invalidate entry, or it can be requesting actually doing a translation, and then if it's being asked to do a translation, your internal state, right, in the state machine, first go to reading the partition table, right, and then so you go from the partition, reading the partition table, and then when this one has turned valid, then you're going to go to the state of reading the process table, and then you're going to go walk through these things. And I guess at the very end you do this segment check. If we can look at partition table read, right? So what do we? So you know, if we get that command to translate an address, then we go to this, and so when you're in that state, you're going to make a request to the data cache. So if we go to the very end of this, right, the valid. Oh, did I lose my connection again? I hope not. You can still hear me, right? Can you still hear me?
Yes, yes.
Yeah. Okay. So you saw this just now, right? This DC request was being set to 1, that goes to the out valid, goes to the data cache, right? And it's going to it's going to come back with you know, with data for, you know, at that address that you're requesting. So now we need to still see where the you know, there's a, you know, there's this base, it's you know, there's some offset in the partition table indexed with the logical partition ID that you know, we should be able to find that is being set. Let's see if there's so the oh, I did. Maybe LP. It is a bit tedious, I have to say, you know, so okay, let's go back again to this partition table. I think maybe oh, okay, yeah. So this is actually where the address is being set, right, for these, you know, corresponding to these different things that you might have to do. So if you're accessing the partition table, right, in this process, the address that goes up to the D cache is being set, and you can see that indeed, right, for the first thing that you're doing, the partition, where you're going to do the access the partition table, the address is going to be set to this here in the PTCR, right? So the relevant bits here are being set, right? So that then means that you know, we saw this being set someplace. We saw just that the address indeed got set to this you know, some bits of the PTCR. That's going to go up to the data cache, and then it's going to come back with you know, with valid data, and then so the data comes back in this variable data, and let me show you somewhere over here. So I mentioned, right? So the in data is the data that comes in that interface from the data cache, and then here is this comment that I mentioned earlier, where it says that the radix 3 data structures in memory are big endian. So that must be, that must be for historical reasons. So you see this byte swapping here. So Sanket, I think you may want to I don't know exactly how things work for Bookie, but at least here there seems to be still, even though microwatt is a completely well, it is by endian, but you by default run it with this little endian Linux. There's still, this indicates that the entries of these tables are done in a big endian way. All right, so right, so that's right, we were here, right? So when you go read that first partition table, right, you set the request to a 1, you indicate that you're going to read. You saw in this other place that the address that you're going to read from was going to be set based on the PTCR, and you go into the wait state, which means you're now waiting for data to come back from the data cache. In that wait state, of course, just stay there until indeed data in done is 1, and when it is done, then you can this partition table, you have an entry for it, right? And you indicate that you are that you are done. And you're going to get a shift amount from from the last, I guess, the last 5 bits of this this data. And then you go to the next one. So now we have to read the process table. So again, we're going to make a request to the data cache. We go into that wait state. We have to look down here for the address that it's actually going to pass on. So if we're reading the partition table, the address that we're going to provide is the PR table address, which hopefully we had up here. Okay, I'm gonna have to look for that. Oh, here. PR table address. So yeah, so it picks up a bunch of bits, from the from the thing it got back here, right? From the partition table, you know, which points to a base, right? And then based on the process ID, you're going to, you know, calculate some offset into this process table, right? Which is where you're actually going to look. So that's what happened. That's what's happening here, right? So there's I don't know the difference between. Okay, here it says effective process ID. I guess it's either 0, you know, based on that address, last address bit, you know, or it's just the process ID, and you know, basically what's happening here is you're calculating an off, you know, where in that table you have to be, right? So then it's again going to go into a wait state, you know, while accessing the data cache again. It's going to be okay, that's here, and then I think maybe this thing is indicating whether you're in supervisor mode and effective is equals real. So it must be something like that, you know, whether you're doing this page table 3 or page table 0. I think the page table 0, I think, is the default case, right? So now we've gone through here. You got this data, and now we're going to walk through those radix page tables, and basically you're going to, you know, this M bits is going to indicate you know how and it also affects, I think, the shift amount. So when M bits is 0, then it actually means you've gone through these different you know, all of the 4 accesses. So I don't know if we can find M bits back up here in that shift thing here. No, that must be indirect. Oh, sorry. Maybe the M bits are used for the masking part. So it's these 5 bits, and it's the next bits up that you're using for this shift, you know, shift amount. I guess but the deal is that when M bits is 0, you know that you're done. And then you go to that. So to the I think there must be still a little bit more detail about the. So in a second we'll look for some of those states that are associated with walking, you know, each of those radix page tables, and then at the end you do this segment stack check, which is yeah, I think just doing some checks on that last address that you got back. Predicts lookup. So not immediately seeing how you make the transition from reading the, that process table to, I mean, here it kind of looks like you go directly from that to radix finish, but that can't be the case. You have to go through these stages here. So it's checking on privilege state. Oh, sorry. I think I see it now. I guess you go to the segments, the segment check, and then the radix lookup. Maybe that's what's happening here. Yeah. Yeah. So let me look for this. Yeah. So I guess the segment check always comes first. That must be the case. So when you go to this radix lookup, again you set this DC request. The request to the cache to 1. You go to the radix wait state. If we go look back at the address assignment, I guess we're in the else case here. So it's going to be the page table address. So we can look for PG table address. That's set based on the base PG. Right, and FPGA. Yeah, so okay. I found, so we go back to this, right? I for the process table, I found how based on this and your process ID, right? You did a calculation with a base and an offset in the table, and then you found a particular entry. There's the same thing here, right? I think this page table thing is the base for this. Then again, there must be a calculation, you know, to come to a particular offset in that table, and you're doing essentially the same thing that you did there. I think the one thing I still wanted to try and see if I could find is that you must be making a transition back into the radix lookup state. You know, if you're not, yeah. See, so it's not. You know, it's not until, I mean, these mask bits change, and it's not until they reach a particular state that you go to radix finish. But otherwise, you know, you go back to radix lookup, and then you know, basically access the next one of these tables. And again, I you know, I think, you know, with a few more hours here, I could probably get to the point where I really do understand every line of it. But I hope that this was a bit helpful, at least in terms of, you know, understanding the structure of how this you know, how this MMU works. But because of how it's written, unfortunately, it's there's a lot of back and forth jumping in the code involved, right? Because the state transitions are in one place, and then the assignments of the addresses are in another, right? And they, you know, everything, of course, you know, kind of happens at the same time. But I hope, you know, you understand the structure with the commands and actually the results coming between the load store unit and the MMU. So that's one interface, and then the interface to the data cache, right? This data command valid signal that goes up there, data coming back from the data cache, and you go through that multiple times, you know, where you go to a read state, a wait state, and then you're done with this thing, and then you go to the next page entry, and then you know, based on base addresses and whatever, you know, pointer you got from a previous entry here, you know, you go into the next page table. And then for those last 4 radix tables, it's different bits of the you know, it's the previous pointer plus some manipulation of a different set of bits from your virtual address, you know, that tell you which entry of the next radix page table you need. So I think the next thing we would want to do is look at A2O. You know, look at what interfaces the MMU has there, right? Hopefully, you know, it's going to do the same basic thing, which is go from a virtual address to a physical address and produce a new page table entry. And then the MMU always is going to have to access the data cache. Sometimes it does that directly. Sometimes you kind of go back through the load store unit. So we'll have to see how that's done in A2O. And then if we get our head around the interfaces there, then we, I think, can go through the process of actually, you know, making this fit in A2O. And at that point, I think we will want to understand every line in this thing. So I think from my side, I wanted to leave it there for today. If there's questions, I can try to answer them, right? But don't, you know, I hope I kind of got the structure of this thing across, you know, the actual bit shift amounts and which bits are getting masked and all that. You know, I haven't, you know, I haven't gotten through that myself yet. So that would have to wait for some future thing, if it's important, right? Because we may be able to just copy it without, you know, as long as we do the same thing, it would be okay. So, any questions? And if not, anything else we want to discuss?
One doubt. We don't need to do cache. All we need to do is the MMU, the TLB, VRAMs, and the virtual to physical address mapping, the whole entirety of it.
No, so basically, you know, the business about the caches and different kind of caches and how the instruction cache worked and the data cache worked, right? And just seeing an example of a translation cache. I hope that was kind of helpful background, right? And you got more background when you listen to those talks from Onu or Mutlu. But no, in A2O we are going to. I don't, you know, other than that, maybe there's some bits we need to carry in a TLB entry in A2O that may or may not be there. But fundamentally, we're not going to touch the caches. We're not going to touch the TLBs or ERATs, right? I hope that the only thing we need to change is the MMU. But the way the MMU is hooked into A2O could be a little bit different than the way it is hooked into microwatt, right? So, for example, the fact that the MMU gets its commands via the load store unit, that is not always the case. Sometimes it's, you know, there is the arbitration between the different things that could be asking for, because you can miss on the I side and you can miss on the D side, right? And then you know, there's at least two pages, two places that an address translation, you know, a request to come up with a new entry can come from, and somewhere you have to arbitrate between those. And in microwatt, it's being sent through the load store unit. But in other processors, that arbitration may happen in the MMU itself. So I think the next thing we want to do is actually look at the MMU in A2O, see which interfaces it has, right, and then see, you know, that'll make a change in how straightforward it is to bolt the MMU in there. But this process of, you know, accessing the cache and getting the next pointer and manipulating it based on, you know, the logical partition ID, the process ID, the bits, you know, 4 sets of bits from the virtual address, you know, to walk through those 6 levels of tables, that's going to be, you know, exactly the same, right? Except that we might have to translate from VHDL to Verilog. So I think the bulk of the code is going to be one for one equivalent. It's just that some of the interfaces, I think, are going to be a little bit different.
Another doubt is that this is more of I don't know what I'm like doing apart from watching lectures and getting to know the code. I like want some clarity on what I'm going to do. That's why like
yeah. So okay, so at some point, right, you're going to you know, a concrete task is going to have to basically recode the MMU so it can fit into A2O, and a bunch of that is going to be, you know, PHDL to Verilog translation, and then the other that maybe that'll be a first. Well, first we will want to see what the interfaces are, but then if we decide they're similar enough, then maybe we can start on a bunch of that translation work, and then, you know, the other pieces that we're going to have to, you know, adjust the kind of the outer parts of the MMU to interface with the rest of A2O. Yeah.
or I do understand. Thanks.
Good. And again, I may be, you know, I might be on a short vacation next weekend, so I'll use the Slack channel to keep you all posted.
Yeah. So if you are not available next week, it's fine, Peter. We can have it following week.
Yeah, maybe it's the better thing to do is to, yeah, but then the week after I'm on a plane. So let's talk a little bit.
Yeah, you can let me know later. You know, that's fine.
Yeah, because
based on your availability and other stuff, you know, we can.
Yeah, because I wouldn't like this, like, because next weekend I'm supposed to be hiking someplace. I might be back early enough to do this, but I might not. And then the week after I'm on a plane back to the US, so that doesn't quite work either. So let's have a communication in the Slack channel to find.
Okay, sure, no problem.
Because I don't think we should wait 2 weeks, but maybe there's another day.
Sure. I think Sanket, you know, will continue that, you know, the FPGA stuff. That will be a good one actually. Once he has done with it, we'll see how we can. Even I'm going to invite Paul to this meeting, you know, to see whether he can help here. Anything.
Yeah, I think Paul is going to be mostly helpful for Sanket. I'm you know, I think the MMU piece, you know, I got through 60-70% of it right now, and I'm sure I can understand the other 40%, you know, of how it's actually built, right? Because, you know, the code does what it does, right? But especially when you talk about what kernel patches might be necessary to make A2O work the way it is right now, I hope that pointer to some of the Freescale processors that I think are at a somewhat similar level. I hope that will help. But if that doesn't help, then I think you know, there's going to be some very OS kernel centric discussion that maybe Paul could help Sanket a lot. But I'm not sure I would try to fold it into this meeting. You know, I don't. I mean, you're of course welcome to ask Paul, but I'm not sure that that's the best use of his time.
Okay, no problem. We'll see how we can